their work on agent factories for chip design. And so Abhishek is an AI research engineer at IBM, and he made foundational contribution to LLM post-training. He was a founding member of Instant Lab, and now recently started working on hardware optimization for chip design using AI agents. Akash is the director of Core AI at IBM, and he works like on he leads research and product on agent ops. And before it was like the founder of the AI innovation team at Red Hat, and before it, he was a researcher at the MIT IBM lab. So during the last few months, we have seen the rise of coding agents, and of course, we have seen how disruptive they've been in the software industries, but in general, in any fields where like software and writing software is a bottleneck. And recently, there's been like people have started trying, researchers and practitioners have started trying to use these coding agents to solve like real world problems and to solve, for example, like optimization problems. So today we're going to see we're going to see like an application of coding agents in the field of chip design, and in particular like on how like coding agents, how far coding agents can be pushed and they can go for our hardware optimization. So Akash, feel free to start.
Yeah, so the way we have thanks, Giorgio. The way we have structured this a little bit is what we are mainly presenting today is this work we did on as two complete domain non-experts on chip design. I think Abhishek and I were sort of like thinking about we've always heard how some of our mentors have told us that this domain requires a lot of like expertise, and without knowing the actual process, without having done it ever, it's probably hard to kind of make any dent here. And so this was kind of like a like a project that happened because we just wanted to figure out like, hey, where have these coding agents, as Giorgio was saying, has actually reached. And we know that this is kind of a lot of proprietary data goes into chip design and so on and so forth. So like, we just wanted to figure out if it is possible to have these agents create a solution for the field of chip design. And I think I will leave a lot of the details for Abhishek to cover, who will deep dive into exactly what the problem was, what we solved, how we solved it. But the notion that we started off on was like, hey, let's just start with like the model itself, right? So maybe just let me share the screen. I'm going to take 15 minutes and talk about this sort of slightly more general idea of how we have been thinking about this, and let me know if my screen is visible.
Yeah.
Is it? Okay. Is it still visible?
Yeah.
Okay. Yeah. So we were thinking about this problem, and then I think actually last December, we had some thoughts, and since then we've been looking into understanding how far coding agents in general can go just by using the notion of inference time scaling, right? So we're not trying to figure out how to retrain these models. Of course, we can always go there, and I think the guys have put out a bunch of papers recently on how to customize these things again. But this was an effort on just understanding how far do you go by using these coding agents on domains that they're not necessarily trained on. So think about domains like chip design, think about domains like engineering design. And so this is kind of where, like, at least I personally, how I think about it and how we went was, you can start throwing these problems to the model, and they do a very bad job at this because they really don't know the domain, and they don't really know what to do. The next level you can go from there is, and let me see if I have this covered. By the way, there's a QR code here. You can go check what it is. It is essentially the culmination of all the effort towards creating a harness that will allow you to do things like automatic chip design and so on and so forth. I am all over the place right now because I asked the same factory to build these slides, and I'm seeing them. This was an experiment that I wanted to do, and so I'm seeing these slides for the first time myself. Okay, so I mean, a lot of this will not be a surprise to a lot of people, but basically, you start by giving a problem to a model, and the model does somewhat like decent, but not really, but all that great. And then, at this point, I think everybody's very familiar with what a harness is. A harness is essentially any scaffolding that goes around your model, right? And one of the most popular harnesses, as Giorgio was saying earlier, is a coding model, right? And that's really the right way to think about this, right? So Claude Code is probably the most favorite coding model or harness that everybody's very familiar with. There's a few others, but if you're interested in like what essentially like makes this a harness is, a few things like you have a model, tool, context loop, memory verification, a bunch of access to some kind of like, if you're making a coding agent, I think giving them access to bash tool is almost enough to, on top of a model, to typically get this example of, what a coding harness is. And what happened, I think late last year is there was a whole resurgence of this idea of like, hey, Claude Code is great, and for majority, I think 90% of the people using it, it's probably a great tool. But if you start doing crazy things with it, you very quickly realize that it's actually not all that powerful. And as a result of it, there's sort of like better harnesses, if you will, that have emerged in form of skills, spec, meta prompts, right? So I'm putting two examples here: Superpowers, GST. If you haven't tried, GST2 is, I think, built on top of Pi SDK, but worth looking into, right? Like if you're hitting the wall with Claude Code, definitely start looking at these things. And then obviously, the Karpathy's auto research kind of happened, and like, it sort of showed that, maybe we sort of like think about the world in this or this work in terms of inner and outer loop, where the inner loop is the problem you're trying to solve, and the outer loop is the orchestrator around it. So if you're familiar with auto research, I'm not going to spend too much time, but something interesting happened around the same time. Some folks from MIT and Stanford took this idea of like, hey, what if you imagine even auto research, you take the outer loop and start evolving it, right? And so they called it a meta harness. And this was like surprisingly really good in terms of like enabling the auto research type work to go beyond a static outer loop. So I've been sort of thinking about this for a while, and this is kind of like where I started hitting a wall with these like inner outer loop things was one way to think about the state of these coding harnesses is that they're basically static. A lot of them don't even have so they are not stateful. They don't evolve, right? If you have started a project, you want to go back to it, you kind of have to give them a lot of context. Yes, you would argue that Claude has like the Claude.md memory files, and OpenClaw people would also say, hey, it has some kind of like this statefulness mechanisms. Yes, I think they are very rudimentary, and they don't really work like how you would work typically, right? They don't remember things the same way that you remember. It's difficult to come back to, and they don't have this notion of like, hey, I've been doing like 13 projects with this. There are common patterns. How do I take all that pattern, like keep evolving myself? And that's kind of why I started building this like a self-evolving harness. So So that's what this factory is about. You will hear the word factory a lot of time in Abhishek's talk. So I'm basically here to like explain what that really is. So essentially, I think 3 months ago or so, I started doing this challenge where I told myself I'll build one app, one paper, something every single day, and it has to be something that I can use for at least a week, right? So I made a bunch of iPhone apps and things like this, and I realized I was just doing the same thing again, right? Like again and again and again. I had a process that I followed. So what I did after a month is I started recording myself, and like, you can look up how to do that as well. And once that recording was done for a month, I essentially converted that into a persona.md, which is basically like my entire work history of how I do things. And based on that, I created a skill set on Claude, which is this idea of like /delegate. And the delegate essentially is not a coding harness. It's actually a digital twin of me that operates Claude Code for me. And then at some point, it was like, hey, this is really cool. How about if I decomposed it into multiple different agents that all had my personality of how I did things? And as a result of it, we ended up creating this factory, which is basically a self-evolving, stateful, decomposed outer loop harness. If you're interested in how the self-evolution loop works, this is based on a prior work called ACE, Agentic Context Engineering. Actually, one of the early talks in this seminar series was by the first author of that paper. Really good talk. If you haven't seen it, probably go back and check it out. But what it basically did is, I think the factory described it very well. Friday's agent is sharper than Monday's. So what it really does is that as it builds things for me, so like, if I ask it to solve a math problem that, so for example, requires some creative thinking, and then I ask it to solve a physics problem next day, it essentially has learned something from solving the math problem that carries over, even though they live in completely different GitHub repos and so on and so forth. I'm gonna maybe just stop here quickly and then show you one actual example before we get into Abhishek's portion, just to kind of make this a little bit more concrete. I'm sorry I'm rushing through this because and the topic of this presentation is mostly on what Abhishek will present, so I don't wanna spend too much time. If you're interested, ping me afterwards, and I can send you a more detailed talk later on this topic. But here's a problem of like what I was saying earlier. So HMMT, if you're not aware, is like there's a portal called Math Arena. Here you can go. This basically documents the performance of all the models on all the problems, right? And it keeps changing. So like you can select a model and say, Claude Opus 4.6 high, and then essentially you can choose a database and it will tell you like which problem it cannot solve, right? So I picked up this problem, and this problem is like really bad because in 4 runs, none of the runs actually converge on the right answer at all, ever, right? And what I did is I essentially gave this problem to my factory that I showed you earlier, right? And essentially what this factory did is this job now is to create another harness, because it knows that Claude and Claude Code, the Anthropics harness, always fail. So now it is saying that, okay, let me stop doing that. Let me start designing a new harness around it. And so you can see the pipeline that it's coming up with. This was generation 1. In the generation 1, it basically created an explorer, a theorist, a computationalist, who together kind of come up with an answer, then get critiqued, audited, debated, judged on, and the synthesizer would like write the answer together, and some verification happened. Long story short, this generation managed to crack the answer partially, in a sense that Explorer and the computationalist managed to get to the right answer, but then the rest of the pipeline still would fail. And so in the next generation, when it ran again, it essentially looked at everything, what was failing, what was not failing, and started mutating this harness to a different one. And that different one, so this is like round one, where everything technically failed, to round two, where it actually did manage to find another pipeline, which ultimately solved the problem. So just to put it in the context, the model and Claude Code, Anthropic's own harness, cannot solve this problem. But if you change the harness with the factory, they do manage to solve the problem. And I guess, I think that realization was kind of very interesting to me, because I think it sort of goes to prove the point that some of the papers that we have been looking into, meta harness and etc., prove that it is just because the model can't one-shot something, or can't beat these benchmark, it doesn't mean necessarily it doesn't know the answer. And I guess maybe if there's one takeaway that I want you to take from this talk, is that build your own harness for the problem that you have, instead of using generic ones. Okay, so now for a much better example of what this actually can do, I'm going to pass it to Abhishek, who will show you how this kind of approaches can actually design a chip for you.
Thanks, Akash. Let me share my screen. So the way I've structured this portion of the talk is I'll spend some time talking about the problem, explain a bit of background. I don't want to get too much into detail, because one, I'm not an expert, and two, I think we can get lost easily in that. And then I'll jump to the instantiation of the factory that Akash was talking about. And then we'll go over if time permits, I want to go into one example of how it was able to solve it, the way Akash went into one. Okay, so there's just a quick primer on this. So the way things are done when you're designing a chip is either you directly write the code in a hardware language like Verilog, or a growing field is now targeting writing the code directly into high-level languages. So you can express your algorithm in C, C++, because majority of people can code in that. And then you can use a tool or a compiler called HLS that can directly compile a high-level code into a hardware language, like Verilog. And then you have a whole stack to convert that Verilog into an actual, an actual physical chip, right? But for simplicity, just assume that you have a C, C++ code, you pass it through a compiler, the compiler produces a hardware circuit. And the compiler will also give you some feedback, like what's the speed of the code, how much area it's getting into. And I'll get into what those mean. So, as I was explaining, the compiler will give you the two metric. These two metric are the most important one, at least right now. So as a designer, you want to make sure that the latency of the code is low. That basically means how many cycles it takes for your code to execute. Fewer is better. And then the second thing is area. So area is a constraint. When you're targeting a hardware, the hardware usually has a limited resources. So your algorithm needs to fit within those resources. And you might have other constraints, like the hardware is shared by some other module. So you might even have a smaller area constraint. So you have to make sure that no matter what optimization you do, you fit within that constraint. And the general rule of thumb, or not the rule of thumb, but a general trend you'll see is the more optimizations you do, the more area you start taking up, because aggressive optimizations will basically sort of unroll everything and compute everything in one go, but takes up way more space. So these are the two metric we are targeting. So we are gonna optimize for latency. So find the code that gives you the least possible latency while respecting the area constraint that I have, for example. Okay, so how is it done today? So this is a very rough diagram. This is no way indicative of the complete industry, but sort of like a very rough understanding. So say you have a design in C, C++, what you'll have is generally an army of hardware coders. These guys specialize in, optimizing code. They will all in parallel explore different optimization strategies. Now, assume this code is huge. That's where complexity grows and the number of things you can try exponentially explodes, right? So this is an expensive approach because each of engineer is a very experienced person. It's not that easy to scale up by just adding more engineers to this process. And it is possible that they might also sort of get stuck in some kind of optimization loop, and it can get harder to pull them out of it. So, but in high level, this is the optimization process. You'll have a bunch of people trying different types of optimization knobs to find the lower latency solution. And what you're looking for is that breakthrough solution that really reduces the latency down, especially if you have like very specific latency constraints at the end. This is in general known as the design space exploration problem. And it's like a very common thing where most of the industry specializes and spends most of their money. This and testing of hardware. Okay, so as I was saying, there are so in high level, there are two optimization knobs you can tweak with. One is called pragmas and other is simply code restructuring. Code restructuring, if you think about it, is simply, can I refactor the code so that I can reduce the code complexity? So the way, if you go for an interview, they will ask you, can you make this code optimized? Reduce the runtime complexity? It's basically like that. Can I restructure it so that it makes it faster? Like fuse the loops or rewrite parts of your code. The second is pragmas. So pragmas are a C++ construct. They are compiler directives that tells the compiler, do something special with this piece of code. If I add a pragma with hashtag path, it will indicate to the compiler that you need to do something special here. Now, HLS tool comes with its own set of pragmas. And when you add that pragma, it tells the HLS compiler how to compile that part of the code to make it more efficient, right? As a visual example, I have I picked like two easier pragmas. The pipeline pragma and the unroll one. The pipeline is very intuitive. Folks who work on training or like multi-node training will immediately see this as a similar thing they do with multiple GPUs. So like you have a loop, you need to do sequence of computation. With pipeline, what you can do is you can schedule such that when the first operation of the first loop is done, you can immediately start the second iteration of the loop. That way you can reduce the latency of the whole loop by almost, like in this case, it's 5 cycles going from, 10 to 20 cycles. The second pragma unroll is simply saying that I have a big loop. What if I completely unroll it? So like write down each iteration as a separate code block. If you do that, and if you compile it with HLS tool, it will execute each iteration in parallel, literally giving you a single cycle latency. But then this blows up the area. So at the end of the day, what you're looking to find is the most optimal combination of pipelines plus code rewriting that's gonna get your program to work super fast. And this is analogous to folks who work in the world of PyTorch and Triton, where they're also doing similar kind of optimizations, but the optimization target there would be like GPUs. So this is the part I was talking about before, code restructuring. So pragmas will only get you this so far. The most powerful optimization is a combination of both. Pragmas plus, you rewrite the code completely. And that is going to give you the best possible cycles on the target hardware. Okay. So as Akash and Giorgio mentioned, coding agents are sort of have exploded on the software engineering scene. The most value comes because they're able to sort of keep at a problem, keep optimizing it. Right? So if you can clearly specify a target to optimize, the model can keep optimizing for that over and over. Sorry, the agent can keep optimizing for that. So if we do a simple experiment where I give the HLS compiler to the coding agent and tell it that the compiler will tell you the latency and area. Can you keep optimizing for it? Keep making changes and keep optimizing until you find the best solution. It can actually do it. But there are problems such as a single agent might get into a search space where it might get stuck into a simple a simple optimization, and then might not be able to explore a variety of solutions. This is sort of similar to what auto research was doing. So to see visually something like this, if a single agent starts exploring, it can take more to get it out, more human intervention. But when we started this work, we were thinking, what if we get n number of agents to start exploring parallel solutions? So the way you would make them diverse is either you would give them different kinds of directive in the prompt, or the starting point or seed could be slightly different, and then let them explore. And so the aim of the study was, how does the optimization you find at the end of exploration scale with the number of agents, right? So if I throw one agent, if I throw 5 agents or 10 agents, how does that change? Is it actually able to find a better solution if you have this diversity in exploration? This is like a classic exploration problem. And if you see, this is synonymous to what we used to do in the early days of language model, which is, and by early, I mean like almost last year, which was, we used to do inference time scaling, where we would give more token budget to a model and let it sort of think more longer. But now you're bringing that notion into agents and letting it explore more. So this is like, so this is sort of like our workflow for solving this problem. So this is, think of it as an instantiation of the general factory that Akash was talking about, right? So the way you would solve an optimization problem is, in this case, and this is in no way the most optimal way, is one, you'll try to locally optimize, and then the second is you will do global optimization. Local optimization, think of it like break the problem down, optimize like parts of the function, and then try to combine them. Which is global exploration is more like look at the code overall and then try to optimize it across all the modules. So that's basically the difference between these two. So let me show you like how under the hood it looks like. So a C++ design comes in, right? So you have something like a main function, and then you'll have some sub functions, ABC. The first part of the factory will first try to understand the call graph or the hierarchy of the functions. This is important later because knowing how the functions are called is going to help us estimate the final latency. And I'll get to that point. Once you have decomposed the code into sub functions, what we start optimizing each function in parallel. So the factory will spin up optimization agents dedicated for each function. The agent does two things. It will try a bunch of variants where it will try pragmas, code restructuring, aggressive optimization, conservative optimization, everything. And it'll create these variants that you see, V0 to V6. And this can be controlled through the prompt, how many variants you wanted to explore. Every time it creates a variant, it needs to pass a correctness check or a functional test to make sure that the changes it has made to the C code did not functionally change the code. And then the second thing it needs to do is pass it through the HLS compiler to get the latency and the area number, to know that what was the effect of your change to the final metric that you're trying to optimize. So that's the second stage, is you're going to generate this set of, so each function is going to produce this list of variants. And what you're trying to do at the end is you want to find that one solution, right? That is going to give you the best latency number. So for example, I might pick V3, V2, and then say V4 here. And then if I combine those and recreate the file, the latency of that final thing should be lower than before. Now, this can get tricky. So for example, a simpler C code, you can simply add up the runtime for each function. But depending on how the functions are called, it might not be as straightforward, which is why we use a solver to determine that. So let me actually, and by the way, feel free to ask if I'm going too fast or if I'm like glossing over some details.
What's ILP mean?
Integer linear programming.
Ah.
It's the solver, the optimization solver we're using.
So, question, and you can cover it later.
Yeah.
So when you are optimizing or hyper optimizing everything, is there any stage at which something can determine like it's better to sacrifice on this particular function to improve in the other and get more holistic optimization than an individual one?
So that's a good question. The problem with local optimization is that it doesn't have the view across the function.
Right.
But the global optimization is where that limitation is addressed by letting it see the whole function. And actually, some of the optimization comes by combining or fusing functions.
Okay.
So just an example, say your main function here called 3 subfunctions, right? It called the key expansion ones, but then those other 2, it called 10 times and 9 times. So if you want to just get like a rough estimate of what's the latency of main function, you can write it down as a simple linear combinations of that. You would do 10x because you would call that 10x times. And then you can sort of estimate the latency of the main function. Things get complicated when you have functions that don't have dependence. So the hardware, when you actually create the chip, can execute those functions in parallel. In that case, you would have to modify your latency equation to sort of take that into consideration. But once you create this latency equation, you can use that to go back here and find the best possible combination. And you can use like a solver Python package to find that solution. The challenging part is understanding the call graph, the function call graph, and then creating this latency equation. So this is, for all these stages, we instantiate a coding agent that will go and understand the code and then write down the equation for that piece of code. So all these optimizations are done by separate agents, and then a final agent is called to create this latency equation. Once that is done, this part, ILP, is a deterministic part that will take the latency equation, take all these variants here. Each variant has the latency and the area tag to it, and it will find you the best combination, right? So it will tell you that, the variant this, when combined, gives you the best possible latency. Once that is done, once you find these subfunctions, then we launch another agent, assembler agent, that will create the final code that assembles all the function. This part is an agent and not a simple script, because what I found is that if you write a script to combine them, you often run into cases where things break very, very easily. But if a coding agent is given this task, it can easily just combine them into a single C code. So that's the first part, or the first stage, which is the local optimization. What we do is, the second part is global exploration, right? So this is where you will have, so this is where you'll have multiple agents explore the solutions in parallel. To begin that exploration, we want to make sure that their starting point is different. If we give the same exact problem at the start to all 5 agents, chances are they might try to, or they might converge to the same solution. You can introduce diversity by giving different prompt directives. In this case, what we did instead was we went back to this ILP, right? The output of ILP. The output of ILP can be ranked. So the rank 1 would be your best solution, but then rank 2 would be the next best solution. What you can do is you can take the top n solutions from the ILP and then use that as your seed for exploration, right? So if I start n agents, I take the first n ILP solutions, and then each of the corresponding agent gets that as a starting point. In this case, each agent will get the entire C code, not just the part of the code, but the entire thing. And the final directive for it is pass the functional test and get me the lowest latency solution as given by the HLS compiler. And each one of them is given these optimization directives. So you can either find the best pragmas, you can explore code rewriting, you can try to find memory optimizations, and I'll show the example at the end. And finally, you need to make sure that everything passes the evaluation, because anything that does not pass the evaluation, that code needs to be either thrown out or redone. So that's the global exploration stage. Let me show you what happens when you scale the N. So our study basically tries to see how does the exploration, what does the exploration produce as you scale the number of agents. So this is sort of the summary of the results, but let me actually jump into the actual results. What we did was we tried 6 simple kernels from a last year paper that addressed a similar problem. And then we picked 6 more kernels from a benchmark that are more compute intensive.
Hey, sorry, let me just before you get into the results, maybe we just want to connect the dots a little bit of the factory and the scaling part, right? So just very quickly, because we've been using this term, and I think it's very clear to us what it is. But I think when Abhishek was showing the phase 1 and phase 2, the idea really was, or the local or the global optimization, the idea, or at least the way to conceptualize is that process defines the factory. Right, so there is a very specific workflow, or you can call it a harness, or you can call it the inner loop. It doesn't really matter what you call it. But that specific process defines the factory floor. And as Abhishek was saying that, hey, it's not the most optimal. I mean, in fact, this was just the first one that we came up with. You can definitely design better. If you're a chip domain expert, you can probably define a much better one. But there are a couple of points to be made here. One is, why did we choose this kind of a thing? So we both had this idea somewhere that, hey, if you look at what local designers, what most human designers are doing, because humans are very limited by the amount of code they can hold in their context, especially when they're optimizing these things, they tend to go and optimize locally, right? Because it's easier. You can optimize each function. You can optimize it's something you can hold and correlate. But if you're dealing with a piece of code which is 20,000 lines of C, I think it's very, very hard for human designers to easily navigate the design space that is that high dimensional. Right? And that's kind of where the global exploration comes from. And I think one of the results that Abhishek hopefully will show is that that's where we found the most amount of improvement that actually comes from these techniques. So this, what you're seeing on the screen, is what we call the process, the factory floor. And then the reason why we chose the word factory was because now that the process is set, you can scale this with worker agents. And that was the other point that Abhishek is trying to make, is that typically what we recently learned through a workshop is that humans do also tend to, when they're designing, they throw a lot of designers on it. In parallel, but of course, you can never match the scale of an automated system. But that is part of their process. So this is the factory floor. Before we get into the results, what we were testing here is you have to design this in a way that you can benefit from agents that have million token context. And then what Abhishek is going to show when he gets into the result is, if you increase the number of workers doing the same thing, how that scaling really improves the performance trade-off, performance and area trade-off. So I'll hand it back to you, Abhishek, or maybe we can see if there's any questions about the setting.
Maybe just one question about the local and global. So this slide. So here you minimize the latency, right?
Yeah.
So in the global exploration, you constrain the area, you have a budget. You say, given the constraints, I choose the RAM, I choose the solution, that has lowers latency, right?
Yeah, the cool thing, by the way, is that there is a hard area constraint, but that doesn't necessarily mean that it can freely explore anything above, that meets that or gets very close to that area constraint. It is able to find solutions that are also better on area.
I see. Because this was kind of my point. Like, could you do the same, but say, okay, I want the minimum of the area, constraining on the latency,
Yeah.
being, constraining the latency be
that's a good
slower or lower than something.
Yeah, I think you can spin up a version of factory that makes the optimization target as lower area. Do not change the latency at all, or like a moderate.
Oh, yeah,
very
but you
small-
have a iteration on the latency, yeah, something like that.
Yeah. So this one is the other one, but yeah.
And I think like the point about creating the two-stage factory setup, or like harness or whatever you want to call it, or inner loop, is a single coding agent would typically try to directly solve this problem of optimization. And that's kind of a pattern that we have seen repeatedly, especially in scientific and engineering problems, that, and as well as what's an orchestrator, if you're familiar with what that is, code base, is that's where they don't tend to work very well. When the complexity grows, creating a bespoke harness and then scaling that in the 4 experiments that we have done so far seem to give disproportionate improvement over directly applying pre-built harnesses like Cloud Code.
And in one of these boxes, you run the local optimization.
No. So the local optimization was stage 1, where you would separately run it and produce again the complete file.
Yeah.
Right, so by optimizing sub kernels, but then that would form input for the global optimization.
Okay.
That makes sense.
Yes, but then the global optimization, how do you optimize in the global optimization?
So it's the same as before, except now your scope has gone beyond optimizing a single function.
Okay.
Now I can see a function ABC, and I tell it, do whatever you can across all functions, including, say, combining them, using them.
But in the second phase, there is no integer linear programming.
No.
Optimization. Okay.
Yeah. Because you don't need to. Because
No, I see.
I think this is kind of the point that we were trying to make. Actually, this is the same point that I think we'll have to do a better job next time when we explain this. Is our conjecture as to why this outperformed humans, you will see in a bit, is because humans are not very good at optimizing a line, 20,000 line of code directly. Right. I mean, the reason we broke it down into 2 stages is because stage 1 is what typically humans do. And often not even code rewrite is what we learned. That code rewrite is actually very hard for them because it has a longer cycle or whatever. But typically what happens is people run Bayesian optimization, right? Which automatically puts your code rewrites out of the scope. And so one of the ways to think about this kind of work is that coding agents have somewhat, they present this representation space where the code is like a numerical variable on which you can run BL. Right? So whenever you're designing a factory, I think keep in mind that there's at least one principle that if you want to go beyond human limitation is that we can't process, we are limited by a context window, which is much smaller than agents, right? So global optimization helps because this is something that we just don't know how to do very well, right?
The question, and again, we can take this later, but for example, what I'm saying is this from local to global, but then global is affecting local as well.
The global will might optimize parts of the code that local optimizer did across to. Yeah.
So is there like a threshold that you use to determine when to go into the local, or or from the local to the global? Like, is there something there, or is that just the agent determining and going in?
So at the global stage, global exploration, it has independence to optimize the entire C code, not just like the local part. It can optimize anything in the whole code base.
I think your question is, in the stage 2, after doing a stage 2, can you go back to stage 1 and do something? Right? Yes. I think that's a natural question, right? But I think what the way, if you look here, right, like it says second block is code rewrite, and first one is pragma, which is part of the first one. But now we're just saying, so stage 1 is saying, decompose the big piece of code into smaller chunks and locally optimize them all. And then I will, through a deterministic optimization, like integer linear programming, I'll put them together. But this will typically lead to a local optima. So now, after that, we're saying that, okay, well, I mean, it's a good starting point, good initialization for my optimization. Now I will let an agent start from this point and do whatever it wants to do. Change pragmas or code rewrite like it was doing before, or merge 2 blocks, which it could not do before, right? So basically, the second stage is a mix of both stage 1 and 2. So that's why you don't need to go back to it. But you can design a factory floor, right? And this kind of is like the point we're trying to make, that this is our factory, but you can say, hey, maybe a better factory is you basically iterate between stage 1 and stage 2, stage 1 and stage 2, and then until a convergence criteria is met. And this is kind of what you were, I think, saying, right? Like, what is the threshold? And you can definitely design that as well, right? And that's kind of what the other factory that I was talking about comes in. That how you design a floor, you can use and iterate on. You can use that meta harness type thing, which I hope it's clear now. But if not, I mean, I think we can sort of revisit this after the results.
Yeah, you can also let the agent choose like what stage to go. But yeah, that's the meta part of the harness. All right. So I guess so what Akash explained, like this kind of like let multiple agents explore, and then in this study we wanted to see how does as I increase the number of agents, what kind of best solution I can hit, or what's the best latency I can hit as I increase the agents. The hypothesis is as you increase more agents, you might discover better solutions, and overall you should be able to hit better speed up. That's how we are measuring the latency. So let me go to this plot first and explain a bit on like zoom in on one single plot and explain. So what you're seeing here is on y-axis is speed up, x-axis is area, and the star here is the baseline. The speed up is with respect to baseline, as in how much more latency speed up I got with respect to baseline when I optimize my code. The red triangles here are if the kernel or the benchmark came with its own hand optimized code, then I plot it as the red triangle. The yellow square is, or orange square is the results of stage 1. We consistently see that the stage 1 results are actually, they don't actually are able to push to the best possible solution because local optimization is a bit constrained in what it can do. And then the green circles you see are the different numbers of agents. So they're indicated with A4, A2, so 2 agents, 4 agents, 10 agents, and 8 agents. So that's kind of how we've organized it. If the circle around any point here, like the circle outline, indicates that at that point, that's the Pareto optimal solution we are able to find. So this sort of forms the Pareto frontier line of solutions. The general trend, what we saw is as you increase the number of agents, you will start seeing a gain in speed up, but at the same time, for certain kernels, you might hit a plateau. So from going from 8 to 10 agents, you might not see as big of an increase in the mean speed up. It might still be able to stumble across the best solution, but the mean speed up might not always be there. Versus if you go from 2 agents to 8 agents, there's a big jump in speed up. So we had 6, sorry. We had 6 kernels that are heavy on compute, and then we used 6 kernels from last year paper as our sort of like a sanity check of if our method works. These are easier kernels. So the trend we saw is on the easier kernels where the optimization, there's not much room for optimization. Even the smallest number of agents are quickly able to hit that, are able to find that optimized solutions. So the most gains you're going to see are problems where the search space is big, and having multiple agents actually helps a lot. There are cases like, for example, leukocyte and stream cluster, where you're going to see a very, very optimized baseline. What these points specifically are the hand optimized code actually replaced the memory interface. So they did not actually change the code, but simply just made the memory interface being able to read in burst the large amount of input data, and that just gave it a big speed up. Versus what we're doing here is optimizing the actual algorithm versus optimizing any interface.
So ideally, you would like all the plots to be like this AES. Like I see most plots, like what happens is that you increase speed up, but at the same time you also need more area.
Yeah.
But that is what you want, or you prefer something like less area and more speed up?
So
it depends.
So it would depend. Maybe it might not actually be possible to hit that sweet spot. And that's why I have the AES example at the end. There's a very specific reason it was able to discover a very good optimization that reduced the area. So initially it was, I mean, if you look at the exploration part, all its solution, I iteratively increased the area. If I open up the 10 agent one and just look at one.
I see.
But then it finds that one solution that immediately reduces the area. But if you look at some other patterns here, for example, the best solution it found
There
here
was higher.
also gave a very high area.
Why? I mean, is there a reason the baselines? I mean, except that case.
Yeah.
Most baselines, they also are like in the lower left, right? Like they're not that fast, but they don't use that much area.
Yeah, because like most of the optimization will target a loop and unroll the entire loop. So the baseline will have the loop. So it's more area efficient to have the loop, but it's also going to be very, very slow.
Yes. So people optimize for area, and then whatever latency you get.
Yeah. Exactly.
I think like the reason most of the baselines are in the lower level is that I think like and then maybe when Abhishek goes through the AES example is like these are like very non-intuitive solutions to human. Right. So some of these things are like I mean, retrospectively, yes, you can probably tell, oh yeah, this is actually pretty cool. But looking at again, if I gave you like 10,000 line of code, I mean, forget 10,000. If I give you like 1,000 line of code to optimize, you will. I mean, naturally, humans go on to like, okay, divide and conquer, right? Break it down. That's what we've been taught, right? Like break it down, this and that. And of course, like if you spend a lot of time on it, maybe you can find it. But I think if you want to speed up, I think that's like the key pattern we're finding in all design space exploration problems. So, I mean, you know this very well, right? Engineering design, CAD and all that thing. The design space exploration is, essentially how much time you spend, the better you get, right? So this is like, in some sense, like the common pattern here is that this is going to speed that process up a lot more. It's not that humans cannot ultimately, I mean, anybody who's searching this space will ultimately find it. But like, how long is your budget? I mean, if you're an iPhone developer, you have to develop a new phone every year, which means you have to present the designs in like 3 months after the release. Then that's your, you're bounded by how much of that design space you can actually explore. Right? I mean, same thing goes for, inference kernels, or even if you are a grad student and you have a deadline for NeoRips in 6 days.
Yeah.
So, if you were to plot this with a third axis of time, like the time it took to actually find that spot,
Right.
how will it look in general?
So the time should also go down as you increase the number of agents because they're also parallelly exploring solutions. Like, so 2 agents, it is possible that if you let them explore longer, maybe they'll stumble across. So there are 2 problems for 2 agents, which is getting stuck in local optima and the time it might take.
Okay.
So let me quickly jump to AES because we're almost out of time. But I do want to quickly cover this example. So the AES is basically an encryption algorithm, right? And the goal is that can I create a chip out of this encryption algorithm such that input goes in and you get an encrypted text at the end. The goal is that the baseline code that I have takes 132 cycles and sort of has like 94K area. This is like a rough number because the actual area is in terms of like individual components. On the left is how the AES code is organized right now. So you have 2 functions, key expansion, that is gonna take your input key and actually expand it to 176 bytes. It's part of the algorithm. And then the cipher that's gonna take your input text and slowly encrypt it for 10 rounds. Okay, let me actually go to this one. This sort of shows you the overview. So this is sort of showing you like a rough overview of exploration. It starts with simply adding pragmas. So it will look at loops and say, okay, wherever I see loop, let me just add a pipeline pragma. And if you remember, pipeline pragma will schedule the loop such that instead of taking the whole n cycles for that loop of a length n, you might be able to schedule operations in the very second iteration, schedule second iteration even before the first iteration is done. What it first tries these pipeline pragmas, but what it finds is these pipeline pragmas don't actually improve the code latency. And the reason is because the data inside the loop, it's trying to access the 4x4 array. And the 4x4 array is stored in this special component on the chip that only allows 2 reads or 2 operations, read or write. And if you're trying to access 8 elements, the most you can do is in 4 cycles. So you cannot go less than 4 cycles. So the smallest pipeline you can get is with pipeline 4. And with pipeline 4, you're not going to get any latency benefits. That is what it finds. So when it finds that, it then starts aggressively applying pragmas, and it actually hits a small breakthrough. What it finds is, if I take the 4x4 array and just put it in a different hardware structure, in this case registers, that allow me to access any element at any time as many times as I want, my cycle goes down. So now instead of having 4 cycles to access the data elements, I can do it in like almost 1 cycle in one go. And that alone reduces the cycle from 190 cycles to 71 cycles. This is sort of the point where it has done almost everything it can for all the loops, but it has hit this weird boundary where it cannot improve any further by just simply adding pragmas. And the reason is because if you look here, it still has to execute the functions in a sequence. The output of key expansion is used in the subsequent functions. But what it finds is the key expansion processes the entire key in one go, but the subsequent iterations only use part of the key, right? So it is possible that you can compute only the first part of key, save some cycles, and let the rest of the loop continue. And then when the second iteration of the cipher loop starts, it can go and pick the next part of the key. So what it ended up doing is here, basically compressing all the functions into a single big loop where it can schedule these operations. So only compute part of what you need and let the rest of the loop start. The minute you do that, you can now apply pipeline and the whole thing becomes super fast. So you go from 71 cycles to only 12 cycles and your area goes down because now instead of having to store this 176 bytes of key, you're only storing, say, maybe 16 bytes of keys. And that just means that you take up less memory resources and your overall code is super fast. So this is like the type of optimization that is what one wants at the end. Hit the sweet spot between area and the latency. I have 2 slides on limitation, like we only tried a small number of benchmarks. We tried like a single family of coding agents and then like a very limited target hardware. And again, as William was noted that why didn't you try different factory design? So the factory design is in no way the most optimal, but can be improved using the meta loop that Akash described. We have some future directions, expanding the benchmark a bit to have more realistic kernels in there. And then more smarter methods. So like the current iteration of Meta Factory or the factory that Akash has now lets you do a lot of things like put learning through the ACE framework, evolve the hardness better to make it more optimal in search. And then you can also use some standard tools that people use. So for example, the Bayesian optimization that was mentioned, that's a tool that the agent can also use to sort of put some explorations on pragmas while it tries some code rewrites. And then at the end, multiple different model families may or may not give you these different types of exploration. So that sort of remains to be seen. Yeah, that's the slides I have. I can take questions.
Yeah, thank you. Very good. Super interesting. So yeah, it's a little late, but if there are questions online or if there are questions in the rooms. Maybe I have a question. Like when you show the results, when you the example you show about the encryption, like yeah. So this is also like a very basic question. It's like using less memory automatically means using less area.
Oh, that's a good question. So here, the memory bottleneck was that it was using these 4x4 arrays, like state arrays, a lot, and these 4x4 arrays take up a lot of space. So even the key that you see, 176 byte, is like a, I think 16 by something array, and storing that whole thing takes.
But
like
this is
a
not
big
always. So,
RAM.
but this is not like it's not always like.
No,
just
no, it
correlation.
depends
You
on
could use,
the-
you could have like using less area, but with more memory.
Yeah.
I see.
Well, if your input is heavy on data, like some kind of data processing,
You
then
need more
you
space.
would have, you would need a lot of space to store the, that, unless you're only using part of that data, then you can say that the data, the complete array might live in some other memory and you only pull part of what you
I
need.
see. But it's interesting because you never, if you understand that you only optimize for latency and area,
Yeah.
but somehow in this example at least,
Yeah.
you also end up optimizing for memory.
Through the memory optimization, it is able to optimize for, to your.
I mean, but memory optimization was not the target, right? Just to clarify.
Yeah, this is what I'm
Not
saying.
really
Like,
optimizing for memory, by the way. It's just saying, if I do this trick, I get lower latency for lower area.
no, this is my point. Like the memory, it's a sub. Like the system understands as a subroutine, as a sub object.
I think that's where code rewrite problem. So chip design optimization has so as you know, right? Like there was this whole workshop where on this paper a couple of days ago. I think our biggest takeaway from the community, where everybody is like some of the best chip design people in the world, right? Was that the biggest difference between how they have been approaching and how we approach this was it's the flexibility of doing verifiable code changes, code rewrites, right? Like bringing that as part in the optimization landscape is something they don't, and correct me here, Abhishek, you were actually in the room, but my understanding was that they don't think of code rewrite as part of the optimization necessarily.
I mean, they do start doing code rewrite when you have to hit that one small timing closing, but they are limited to how they can scale that effort because
it is more
you-
component.
Yeah, and you need like really talented PD engineers to start looking into that code.
In a way, code rewrite in this framework can do large amount of optimization, but before it was like more like very localized.
Yeah.
By the way,
Like,
also just to kind of put this in context, right? These kernels are like 30-year-old at least, or probably more.
these are
And the fact that ILP cannot even find this solution there's something to be said about that, right? Like it's not like we pick problems that are like humans haven't had enough time or something.
I know it's also that, for example, this would be very interesting also for something like fluid dynamics. A lot of optimization routines are written in Fortran.
Yeah.
And it's not that people just don't want to touch them. People are just it's a lot of effort to like.
So actually, today's talk later,
and stuff like that.
the talk later today on that I mentioned is basically to apply this to other well, specifically like engineering design domains.
Nice.
Simulation and how do you iteratively improve those kernels.
Do you have other questions? Maybe not online. So let's speak again. Thank you, Akash. Thank you, Abhishek.
Thank you.
Thank you.
Bye-bye.
Close it there.
By the way, Abhishek. Oh shit! No, never mind.